Inconsistent enforcement of grounding requirements for generators can be a complex issue. Firstly, it's important to understand the context. It appears that there's a discrepancy in how grounding is enforced for generators, particularly those that function as what are termed subpole generators. These are generators that don't switch the neutral conductor when they take over the load. When evaluating the grounding requirements, refer to National Fire Protection Association 70, the National Electrical Code, specifically Articles 250.32 and 250.50. Article 250.32 addresses grounding and bonding requirements for buildings or structures supplied by feeders or branch circuits, while Article 250.50 pertains to the grounding electrode system. Secondly, analyze the subpanel generator scenario. The core of the issue revolves around whether a generator without a neutral transfer switch, often called a subpanel generator, should be treated as a separately derived system requiring its own grounding electrode. The argument against requiring a grounding electrode for such generators is that they are not considered separately derived because the neutral conductor is not switched. The neutral remains connected to the main service panel, maintaining a continuous neutral path back to the utility source. This means the generator's neutral is at the same potential as the main service neutral. Thirdly, understand the rationale behind requiring grounding electrodes. Grounding electrodes are primarily intended to provide a path for fault current to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers or fuses. They also help to stabilize voltage to ground and limit voltage surges. For separately derived systems, such as generators with neutral switching, a grounding electrode is essential to establish a local ground reference and ensure proper fault current flow. Fourthly, consider the interpretation of a structure served. The crux of the matter lies in how the term structure served is interpreted. The National Electrical Code requires a grounding electrode system for each building or structure supplied by a service. The question is whether a generator supplying power to a building, even without switching the neutral, constitutes a structure served in the context of the code. Some argue that if the generator is supplying a separate building, regardless of whether it's separately derived or not, it should have its own grounding electrode. This is based on the principle that each building should have its own connection to earth for safety and stability. Fifthly, address the inconsistency. The inconsistency arises when a generator is treated differently from a subpanel feed to a separate building. In the latter case, a grounding electrode is typically required at the separate building. The argument is that if a subpanel feed to a building requires a grounding electrode, a generator supplying a building should also require one, regardless of whether the neutral is switched. Sixthly, review code interpretations and expert opinions. It's crucial to consult with relevant authorities and code interpretation panels to gain clarity on this issue. These bodies can provide official interpretations of the code and offer guidance on specific scenarios. Reviewing past code interpretations and expert opinions can shed light on how similar situations have been handled in the past. Seventhly, consider the practical implications of requiring grounding electrodes for all generators. Requiring a grounding electrode for every generator installation, regardless of whether it switches the neutral, would add to the installation cost and complexity. However, it could also enhance safety by providing a more robust grounding system. A cost-benefit analysis should be conducted to weigh the potential benefits against the added costs. Eighthly, promote clear and consistent enforcement. To avoid confusion and ensure fair application of the code, it's essential to have a clear and consistently enforced policy on generator grounding. This policy should be based on a thorough understanding of the code, relevant interpretations, and practical considerations. Inspectors should be trained on the policy and provided with clear guidelines for enforcing it. Ninthly, explore potential solutions. To resolve the inconsistency, several solutions could be considered. One option is to adopt a policy of requiring grounding electrodes for all generators supplying separate buildings, regardless of whether they switch the neutral. Another option is to develop a set of criteria for determining when a grounding electrode is required for a generator, taking into account factors such as the size of the generator, the type of load it serves, and the specific characteristics of the installation. 10thly, consider the role of bonding. In addition to grounding electrodes, bonding plays a crucial role in electrical safety. Bonding ensures that all metallic parts of an electrical system are connected together to create a low impedance path for fault current. This helps to minimize voltage differences and reduce the risk of electric shock. When installing a generator, it's essential to ensure that all metallic parts of the generator, the transfer switch, and the equipment it supplies are properly bonded together. 11thly, understand the different types of grounding electrodes. There are several types of grounding electrodes that can be used, including ground rods, ground plates, and metal underground water pipes. The National Electrical Code specifies the requirements for each type of grounding electrode. The choice of grounding electrode will depend on factors such as soil conditions and the availability of suitable electrodes. 12thly, consider the impact of generator size. The size of the generator can also influence the grounding requirements. Larger generators typically require more robust grounding systems than smaller generators. The National Electrical Code provides guidance on sizing grounding conductors and electrodes based on the size of the generator. 13thly, address the specific concerns. It's important to address the specific concerns and questions that have been raised regarding generator grounding. This may involve providing detailed explanations of the code requirements, conducting site inspections, and working with electrical contractors to ensure that installations are in compliance. 14thly, consider the use of ground fault protection. Ground fault protection can provide an additional layer of safety by detecting and interrupting ground faults. Ground fault protection is typically required for larger electrical systems, but it can also be beneficial for smaller systems, such as those served by generators. 15thly, ensure proper coordination of overcurrent protection. Proper coordination of overcurrent protection devices, such as circuit breakers and fuses, is essential for ensuring that faults are cleared quickly and safely. When installing a generator, it's important to ensure that the overcurrent protection devices are properly sized and coordinated to protect the generator and the equipment it supplies. 16thly, evaluate the effectiveness of existing grounding systems. It's important to periodically evaluate the effectiveness of existing grounding systems to ensure that they are still functioning properly. This can involve testing the resistance of the grounding electrodes and inspecting the grounding conductors for damage or corrosion. 17thly, consider the impact of different types of loads. The type of load served by the generator can also influence the grounding requirements. For example, sensitive electronic equipment may require a more robust grounding system than less sensitive loads. 18thly, address the potential for voltage fluctuations. Generators can sometimes experience voltage fluctuations, which can affect the performance of sensitive electronic equipment. A properly designed grounding system can help to minimize voltage fluctuations and improve the stability of the electrical system. 19thly, consider the use of surge protection. Surge protection can help to protect electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, switching operations, or other events. 20thly, ensure compliance with local codes and regulations. In addition to the National Electrical Code, there may be local codes and regulations that govern the installation of generators. It's important to ensure that all installations comply with all applicable codes and regulations. 21stly, document all grounding system details. It's important to document all details of the grounding system, including the type of grounding electrodes used, the size of the grounding conductors, and the location of the grounding electrodes. This documentation can be helpful for future maintenance and troubleshooting. 22ndly, provide ongoing training for inspectors and electricians. Ongoing training is essential for ensuring that inspectors and electricians stay up to date on the latest code requirements and best practices for generator grounding. 23rdly, promote a culture of electrical safety. Promoting a culture of electrical safety is essential for preventing electrical accidents and ensuring the safety of workers and the public. This can involve providing safety training, conducting regular safety audits, and encouraging workers to report any potential hazards. 24thly, understand the purpose of a transfer switch. A transfer switch is a device that allows you to switch between the utility power and the generator power. There are two main types of transfer switches: manual and automatic. A manual transfer switch requires you to manually switch the power source, while an automatic transfer switch automatically switches to the generator power when the utility power is lost. 25thly, consider the location of the generator. The location of the generator can also influence the grounding requirements. If the generator is located outdoors, it may be subject to different grounding requirements than if it is located indoors. 26thly, understand the different types of generators. There are several types of generators, including portable generators, standby generators, and prime power generators. Each type of generator has its own specific grounding requirements. 27thly, consider the use of a neutral grounding resistor. A neutral grounding resistor is a device that is used to limit the amount of current that can flow in the neutral conductor during a ground fault. This can help to reduce the risk of damage to equipment and injury to personnel. 28thly, ensure proper labeling of equipment. All electrical equipment should be properly labeled to indicate its voltage, amperage, and other important information. This can help to prevent accidental contact with energized equipment. 29thly, understand the dangers of backfeeding. Backfeeding occurs when power from a generator is fed back into the utility grid. This can be extremely dangerous and can pose a risk to utility workers. It's important to take steps to prevent backfeeding, such as installing a transfer switch. 30thly, follow all safety precautions. When working with electrical equipment, it's important to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and working in a safe environment. By addressing these considerations and taking appropriate measures, one can ensure that generators are grounded properly and that electrical systems are safe and reliable.